Welcome to this explainer. You know that giant chart of chemistry you've probably stared at on a classroom wall for hours? Well, today we're going to completely decode it. We're taking it from a confusing, random-looking grid of letters and numbers and transforming it into a beautifully logical, perfectly organized map of the universe's ingredients.
Okay, so here's our roadmap for today. We'll start by fixing the early drafts of the periodic table, then we'll decode the subshell secret, explore the great divide of metals versus nonmetals, meet the distinct families of the table, and finally, we'll learn the rules of reactivity.
Let's jump right into Section 1, Fixing the Periodic Table, from flawed drafts to modern logic. To really appreciate the map we use today, we have to look back at the broken street signs of early scientific classification. Dmitri Mendeleev's early table was an absolutely phenomenal starting point, but he organized his elements based on increasing atomic weight, or mass. And, well, this created some glaring glitches. For instance, argon is heavier than potassium. Yet, based on how it actually reacts, argon had to sit before potassium. It literally broke his own rule. Plus, his system struggled with where to put hydrogen. It completely lacked a proper home for the heavy lanthanide and actinide series. And, most critically, it completely failed to account for a really sneaky atomic variation.
And that sneaky variation? It's the isotope. An isotope is simply a version of an atom that has the exact same chemical properties as its standard counterpart, but a slightly different mass. Why? Because it's carrying extra baggage, literally extra neutrons in its nucleus. Since Mendeleev's whole system grouped elements by their mass, these newly discovered isotopes threatened to break his entire classification system apart. I mean, chemically, they belonged in the same exact box, but mathematically, his mass-based rule said no way.
So what was the fix? The ultimate fix was introduced by a scientist named Henry Moseley. He realized the foundation of the table was just slightly off. By shifting the organizing principle away from atomic mass and instead using atomic number, which is just the exact number of protons in an atom's nucleus, everything just clicked into place. This modern law elegantly solved the isotope issue, because isotopes of the same element always have the same atomic number, meaning they perfectly share a single spot on the table. Problem solved.
This absolutely crucial shift gave us the pristine, logical structure we use today. The modern table is arranged into 18 vertical columns. We call these columns groups. Basically, if you live in the same group on this map, you're going to share very similar chemical properties with your neighbors right above and below you. Intersecting those 18 columns are 7 horizontal rows, and we call those periods. Every single time you move down to a brand new row or period, a brand new main electron shell is being added to the atom. It's kind of like adding a new ring to a tree or an outer layer to an onion.
All right, moving to Section 2, the subshell secret. Let's decode the atomic zoning laws.
Let's zoom in from the macrostructure of the whole table down to the micromechanics. These mechanics dictate exactly where an element is zoned to live on this map. To understand it, we have to talk about electron configurations. Inside those main electron shells I just mentioned, which scientists often call K, L, M, and N, there are specific subshells. Think of the main shell like a massive apartment building, and the subshells as specific apartments of entirely different sizes. We call these the S, P, D, and F subshells, and they have very strict occupancy limits. The S subshell is tiny, with just one orbital holding exactly 2 electrons. The P subshell holds 6. The D subshell has 5 orbitals, holding up to 10 electrons, and the massive F subshell, it can accommodate up to 14 electrons. So, how do these atomic apartments actually fill up? Well, they follow a really crucial rule called the Aufbau principle. This principle basically says that electrons are fundamentally lazy. They absolutely must fill the lowest energy subshells first before moving on to the higher ones. But there's a fascinating quirk here. After filling the 3p subshell, the energy of the 4s subshell is actually lower than the 3d subshell. So, notoriously, atoms require us to fill the 4s subshell first before looping back to fill the 3d subshell. This quirky energy overlap is exactly the reason the middle section of our periodic table is shaped the way it is. Now, these subshell configurations aren't just atomic trivia. They are the absolute secret to determining an element's valency. Valency is essentially the ultimate rulebook for how elements bond and interact with one another. It's the combining capacity of an element, and it's driven entirely by how many electrons are sitting in that very outermost final shell. Do they want to give electrons away to become stable, or do they want to steal them? That single question drives the entire universe of chemistry.
Which brings us perfectly to Section 3, metals versus nonmetals, the table's great divide. With those subshell mechanics firmly in our minds, let's pull back and explore the two vastly different primary neighborhoods of our atomic city. The most crucial point is the stark physical and chemical contrasts split right across our map. Taking up the vast majority of the left side, from groups 1 to 13, are the metals. They're shiny or lustrous, and they are fantastic conductors of heat and electricity. Chemically, we call them electropositive, which just means they desperately want to lose their outer electrons to achieve a stable subshell. Conversely, huddled over on the right side, we have the nonmetals. They are mostly dull, they act as terrible conductors or great insulators, and they are electronegative. They are super hungry to gain electrons to fill out their shells.
But wait, what about the borderlands? Right on that zigzag dividing line between these two extremes live the metalloids, elements like boron, silicon, and germanium. They're weird because they exhibit properties of both. They are semiconductors, meaning they only partially pass electricity. And this isn't just some fun science fact. This exact semiconducting property is why metalloids like silicon are the absolute vital foundation for manufacturing computer microchips. Literally, the device you are using right now works because of exactly where silicon sits on this map.
Section 4, families of the table. Let's explore some distinct neighborhoods. See, the elements aren't just broadly grouped into metals and nonmetals. Elements in the exact same vertical column act like close-knit families, sharing identical outer valency traits. Starting on the far left, we have Group 1, the alkali metals. This is your lithium, sodium, and potassium. Because they have a valency of exactly 1, literally just one single electron hanging out in their outermost S subshell, they are desperate to ditch it. This makes them incredibly reactive, so much so that they violently explode upon hitting water, releasing hydrogen gas and forming water-soluble bases called alkalis. Sitting right next door in Group 2 are the alkaline earth metals, like magnesium. They have a valency of 2, making them slightly less reactive than Group 1, but still highly prone to forming basic oxides. Bridging the gap right in the middle of the table, Groups 3 through 12 are the transition metals. Remember that quirky rule where the 4s subshell fills before the 3d subshell? Well, these elements are exactly where those d-block subshells are finally getting filled up. This unique electron configuration gives us dense, hard elements with incredibly high melting points. This is where you find the heavy-duty stuff, right? Iron, copper, zinc, and gold. Now jump over to the far right, and the families shift drastically. Group 17 houses the halogens, like fluorine and chlorine. These are nonmetals that are missing just one single electron to complete their outer p subshell. That makes them incredibly aggressive and reactive, essentially hunting down that last electron anywhere they can to gain stability. But look right next to them in Group 18. This is the finish line. The noble gases like helium and neon. Their outer subshells are perfectly, completely full. They have a valency of 0. Because they don't need to lose or gain absolutely anything, they are completely chemically inert, unreactive, and totally independent. Let's wrap things up with Section 5, the rules of reactivity, predicting chemical behavior. For our final stop in this explainer, we really need to understand the overarching trends here. Because once you grasp the mechanics we've just talked about, simply moving your finger across this map allows you to accurately predict how aggressively any of these atomic residents will behave. Let's look at what happens as you move vertically down a group. Atoms get bigger because they're adding entirely new electron shells. For the metals on the left side, getting larger makes them far more reactive. Why? Because metals want to dump electrons, and when an atom is huge, its outermost electrons are way farther away from the pulling force of the nucleus, making them super easy to lose. But for the nonmetals on the right side, the rule is totally flipped. Because nonmetals want to grab electrons, getting larger actually weakens the attractive pulling power of their nucleus. So nonmetals get less reactive as you go down the column. Which brings us to a really fascinating conclusion. Knowing that metals want to lose electrons, and knowing that atoms get larger and more reactive the further down a group you go, just imagine Group 1 for a second. We already know that sodium and potassium near the top are highly reactive, literally bursting into flames when they touch water. It makes you wonder, doesn't it? Just how staggering is the explosive potential for the massive, highly unstable elements lurking at the very bottom left corner of this beautifully designed map? What happens when a giant like francium meets water? That is the incredible predictive power of the periodic table, and I really hope this explainer has left you eager to look at that classroom chart with completely new eyes. Thanks for joining me.